Hello everyone! Today we continue with one of the unsupervised learning methods in our machine learning journey. So far, we have covered k-means clustering method as an unsupervised learning method. Before that, we have covered supervised learning methods. As you remember, supervised learning methods have a broad literature and probably the most popular machine learning methods in practice. So far, we have seen quite a number of machine learning models including decision trees, neural networks, and support vector machine, which is a well-used method in machine learning area. We learned the theory behind the methods and also their work in practice. You can see those videos using the link above. Let us start. As you remember, we have two types of learning algorithms classes, supervised and unsupervised learning. So far, we have seen supervised algorithms. Now we move on to the other type of learning tasks that falls in the class of unsupervised learning. This time, we again have our data points, however, without y values. So there is no associated y values in our data. In this setting, we are some sense of working blind. This is referred to as unsupervised because we do not have a response variable that can supervise our analysis. What we do is that we seek to understand the relationships between the variables or between the observations. As said in the previous slide, there exist only x values without their response variables. With unsupervised statistical learning, there are inputs but no supervising output. Nevertheless, we can learn relationships and structure from such data. In general, we can cluster observations on the basis of the features in order to identify subgroups among the observations. Or we can cluster features on the basis of the observations in order to discover subgroups among the features. Examples include customer segmentation, which is a clustering task. Suppose that you are a manager of a store and you want to know your customers better than ever. How you could do this? Of course, it is not possible to focus on each individual. What you can do is that you can group individuals by looking at their similarities. This operation is called clustering. Fraud detection and some of the medical imaging can also be given as examples of this kind of learning tasks. Hierarchical clustering is a simple and elegant approach for partitioning a dataset into distinct, non-overlapping clusters. Comparing to k-means clustering, hierarchical clustering does not require to commit a particular choice of k. Thus, number of clusters can be specified after performing the clustering operation. Hierarchical clustering has an advantage over k-means clustering, which it results in an attractive tree-based representation of the observations, which is called a dendogram. There is a common approach to construct a dendogram, which is bottom-up or agglomerative. This is the most common type of hierarchical clustering, and it refers to the fact that a dendogram is built starting from the leaves and combining clusters up to the trunk. We will see an example of a dendogram in the following minutes. The term hierarchical refers to the fact that clusters obtained by cutting the dendogram at a given height are necessarily nested within the clusters obtained by cutting the dendogram at any greater height. We will introduce the hierarchical clustering algorithm. We start with defining a dissimilarity measure between each pair of observations. This is generally selected as an Euclidean distance. However, there are multiple of them. The algorithm proceeds iteratively, starting out at the bottom of the dendogram. Each of the n observations is treated as its own cluster. The two clusters that are most similar to each other are then fused so that there are now n-1 clusters. Next, the two clusters that are most similar to each other are fused again, so that there are now n-2 clusters. The algorithm proceeds in this fashion until all observations belong to one single cluster, and the dendogram is complete. As you can see, the algorithm is pretty simple, but one thing is not addressed yet. We define a dissimilarity between pairs of observations, but we did not define the dissimilarity between two clusters. What happens if one or both of the clusters contains multiple observations? The concept of dissimilarity between a pair of observations needs to be extended to a pair of groups or observations. This extension is achieved by developing the notion of linkage, which defines the dissimilarity between two groups of observations. The four most common types of linkage: complete, average, single, and centroid. In complete linkage, we define the distance between two clusters to be the maximum distance between any single data point in the first cluster and any single data point in the second cluster. Based on this definition of distance between clusters, at each stage of the process, we combine the two clusters that have the smallest complete linkage. In average linkage, we define the distance between two clusters be the average distance between data points in the first cluster and the data points in the second cluster. So at each stage of the process, we combine the two clusters that have the smallest average linkage in distance. In single linkage, we define the distance between two clusters as the minimum distance between any single data points of the clusters. Thus, at each stage of the process, we combine the two clusters with the smallest single linkage distance. And last, in centroid linkage, the distance between two clusters is the distance between the two mean vectors of the clusters. So, at each stage of the process, we combine two clusters that have the smallest centroid distance. So, in our algorithm, we begin with n observations and a measure, such as Euclidean distance, of all pairwise dissimilarities. We treat each observation as its own cluster. For I, starting from n till 2, we do the following. Examine all pairwise intercluster dissimilarities among the I clusters. Then identify the pair of clusters that are the least dissimilar, which is the most similar ones. Then we are going to fuse these two clusters. The dissimilarity between these two clusters indicates the height in the dendogram at which the fusion should be placed. And lastly, we compute the new pairwise intercluster dissimilarities among the I-1 remaining clusters. Let us have a look at the dendogram, which is a result of a hierarchical clustering algorithm. I took this dendogram from an internet source. Each leaf on the dendogram represents one of the observations in our dataset. However, as we move up the tree, some leaves begin to fuse into branches. These correspond to observations that are similar to each other. As we move higher up the tree, branches themselves fuse, either with leaves or other branches. The earlier fusions occur, the more similar groups of observations are each to other. On the other hand, observations that fuse later can be quite different. In fact, this statement can be made more precise. For any two observations, we can look for the point in the tree where branches containing those two observations are first fused. The height of this fusion, as measured on the vertical axis, indicates how different the two observations are. Thus, observations that fuse at the very bottom of the tree are quite similar to each other, whereas observations that fuse close to the top of the tree will tend to be quite different from each other. Therefore, we cannot draw conclusions about the similarity of two observations based on their proximity along the horizontal axis. Rather, we draw conclusions about the similarity of two observations based on the location on the vertical axis, where branches containing those two observations first are fused. There are some practical problems regarding the clustering methods and also hierarchical clustering. First, should we standardize the observations or features in some way? Or what dissimilarity measure should we use? What type of linkage should be used? Or where should we cut the dendogram in order to obtain clusters? Each of these decisions can have strong impact on the results of the clustering method. What best in practice is that we try several different choices and look at the one with most useful or most interpretable solutions. With these unsupervised methods, there is no single right answer in a solution that exposes some interesting aspects of the data should be considered. Today, we'll learn one of the unsupervised learning methods, hierarchical clustering algorithms. We introduce the mathematical problem together with the notion of linkage. We would like to hear what you think about our content. Thank you for watching our videos. Please do not forget to hit the subscribe button. By doing so, you are really helping us to grow. You can always ask questions by leaving a comment below, and we will be happy to answer it. In our next video, we will cover principal component analysis. See you in our next videos. Bye bye.